So we're very happy to kick off the afternoon session with Suvrat Raju, who will tell us about a toy model for the information paradox in empty space.
Okay, so thank you very much, first of all, to the organizers for inviting me to this wonderful meeting. I hadn't used my winter jacket for many years, so it's a pleasure to get to do that as well. Let me just start with some motivation and a summary of what I'm going to talk about. So the purpose of this talk is to present a toy paradox that I think very closely resembles the paradoxes regarding monogamy of entanglement that arise during black hole evaporation. And the main technical tool I'll try and use is I'll phrase the monogamy of entanglement not in terms of the von Neumann entropy as is often done, but in terms of the monogamy of Bell correlations, which is, I think, a technical tool that hasn't been used enough in this entire discussion. And the advantage of using Bell correlations as opposed to the von Neumann entropy is that Bell correlators can be computed reliably within effective field theory because they're just low point correlation functions. And this, I think, leads to a toy model that in a very clean way demonstrates how, at least in this example, the loss of locality in quantum gravity can look like the loss of monogamy of entanglement. Okay? We can argue about the significance, but I think that at least this example is a very clean example that deserves some attention. So let me remind those of you who are not familiar with how these monogamy paradoxes go. So these monogamy paradoxes really started with the work of Mathur in 2009, and then which was elaborated by Amps a few years later. And what Mathur and Amps pointed out was that if you take a black hole, evaporating black hole, and you look at it after its page time, then the Hawking radiation that's emerging just at that time, due to the page argument, has to be entangled with the old Hawking radiation, but it also has to be entangled with the region behind the horizon. And this leads to a violation of the strong subadditivity of entropy, which says that this region B can only be entangled either with A or with C and can't be entangled with both. In fact, this strong subadditivity paradox you can think of as a more precise and a somewhat embellished version of an older paradox, which is called the cloning paradox, which goes as follows. You draw a nice slice that tilts up, and so it captures a lot of the outgoing Hawking radiation. And then this Hawking radiation has to have information about the infalling matter, but you can argue that the nice slice has to intersect the infalling matter as well. So it looks like the same information is present at 2 points on the slice, which would suggest that there's cloning of quantum information, which of course is disallowed by quantum mechanics. So these two paradoxes are very closely related to each other. In fact, in previous work, a lot of it done with Kyriakos, we proposed that, following older ideas about complementarity, that one way to resolve this paradox would be to say that the operators that live inside here at x in are actually should be identified with some complicated polynomial of the operators that live outside. And if such an identification exists really, then of course one would say that locality is lost because the degrees of freedom here are complicated rewritings of degrees of freedom there, but there's no violation of monogamy and there's no cloning. So that would be the proposed resolution. What I want to describe in this talk is that how something like this is not special to black holes, but even occurs in a very simple setting where we think we understand everything, which is just empty anti-de Sitter space. And as I said at the beginning, the advantage of this model that I'll present is that everything is under control and it's a very clean calculation. And so one can argue about its significance, but I think it presents a clean potential answer to these paradoxes. Okay. Let me just say one more caveat before I go forward. In fact, in the original proposal that we had with Kyriakos, this loss of locality, this identification, appeared with some other physical effects. One of them was state dependence, and then we had to postulate some small, non-perturbative, exponentially small corrections to Hawking radiation. In fact, while state dependence and these exponentially small corrections appear to be important for understanding black hole evaporation, in this talk, I am not going to invoke either state dependence or these exponentially small corrections. So if you don't like state dependence, I'm happy to argue with you after the talk. But in this talk, I'm going to talk about this loss of locality without invoking any of these other effects. Okay. So let me remind you about how the monogamy of Bell correlations goes. So first, let me just tell you about Bell inequalities. Okay? So Bell inequalities go as follows. So the idea is to consider two observables, or two pairs of observables, which we'll call A and B. And then within A, there are two operators, A1 and A2, and B1 and B2. And it's important that these operators are bounded operators. In fact, the convention we'll choose is that their operator norms are less than 1. Okay? So the largest eigenvalue is 1 or minus 1. And these operators commute with each other. So you can think of them as operators in different systems. And then the idea is to define this thing called the CHSH operator after the people who invented it, which is this particular combination. And it's easy to persuade yourself that classically, if A and B are classical random variables, the largest value this C operator can take is 2. Okay? But quantum mechanically, in fact, C can be larger than 2, and it can be as large as 2 root 2. Okay? So in particular, if the CAB is between 2 and 2 root 2, then that means that A and B show correlations that go beyond classical correlations, which is a statement that A and B, systems A and B, are entangled with each other. Okay? So when I say that systems A and B are entangled, it means that these correlations are between some value of 2 and 2 root 2. Okay. So how do you talk about the monogamy of entanglement in this language? The idea is to consider a third pair of operators, which are C1 and C2, and they have the same property. Their operator norm is less than 1, and these C operators, they commute with A and they commute with B. And then Ben Toner and Francois-Stratti proved a really nice result in 2006, and they pointed out that if you now construct CAC in precisely the same way that we constructed the CAB operator, then the square of CAB plus the square of the expectation value of CAC is always less than 8. Okay? And what this means, notice, is that if A is entangled with B, which means that CAB is larger than 2, then you see that CAB squared is larger than 4, and therefore CAC must be smaller than 2. Okay? In particular, if CAB is 2 root 2, which is the largest allowed value, then A and C cannot be correlated at all. Okay? So you see that if A and B are entangled, then A and C cannot be entangled. Their correlations have to be less than the allowed classical limit, and therefore this is a very nice statement of the monogamy of entanglement phrased entirely in terms of 2-point correlation functions, and this is the key inequality that I'm going to use in this talk. Okay. Now, in a quantum field theory, in a local quantum field theory, remember there were some conditions that went along with this. The operator norms of these operators had to be less than 1, and then these operators had to commute. But in fact, in a local quantum field theory, you can replace the statement that these operators commute with the statement that these operators A, B, and C are supported in regions which are space-like to each other. Okay? So if A, B, and C are supported in space-like separated regions, then in a local quantum field theory, they have to commute with each other. And therefore, all you need to say is that the operators A, B, and C are bounded by 1, and they're supported in space-like separated regions. And if this happens, then you have the statement that CAB squared plus CAC squared is smaller than or equal to 8. Now, when you go to gravity, you of course immediately end up with the problem in generalizing the previous statement that there are no exactly local gauge invariant operators in gravity, which we know. So for the purpose of this talk, I'm going to talk about what I'll call a localized operator, which is not necessarily a local operator, okay, but it's a localized operator. And that's a naive notion of what we mean by a local operator. So what I'm going to talk about is going to be a function of field operators that come from a region after one has made a particular choice of gauge. And I'm not going to specify the choice of gauge except at one point, because in most cases it's not going to be important. Okay, so this is what I'll call a localized operator. That's my definition of the term. And the statement I want to show you is that in gravity, if we take A, B, and C to be localized operators, to be localized on space-like separated regions, then, and of course to be bounded, operator norms to be bounded by 1, then this monogamy inequality is violated, and not violated by a small amount, but you can violate it by an order 1 amount, and that's what I'm going to try and demonstrate. Okay. Okay, so before I go into gravity, let me just try and explain how these Bell correlations work in quantum field theory, and then we'll introduce the effect of gravity. Okay? Okay, in fact, before we do quantum field theory, it's convenient to just think about two simple harmonic oscillators. So let's take two simple harmonic oscillators, and various points in this talk I'll have these alpha operators. These are just the annihilation operators. Alpha dagger is the creation operator. And think of two simple harmonic oscillators in this thermofield state, which is taken by taking the joint vacuum and exciting it by this exponential of alpha dagger, alpha A dagger, alpha B dagger. And then in the state, I'm going to denote PA to be the projector onto states which are annihilated by alpha A. So PA, as I said, projects onto states which have occupancy 0 for the A-type oscillators, and PB projects onto states which have occupancy 0 for the B-type oscillators. And whenever you see this index S, it always runs over either A and B, and if there's a system C, it runs over C as well. Okay, so it's the system index. And then you define these operators A and B, which are defined in this way. In fact, these expressions look complicated, but they're pretty simple to understand. What this operator A1 is doing is it's acting like sigma Z within the space of states which have occupancy 0 in NA and occupancy 1 in NA. Okay? So it's acting like sigma Z in that two-dimensional space, and what A2 is doing is acting like sigma X within that space, and B1 is acting like sigma Z plus sigma X in the B space, and B2 is acting like sigma Z minus sigma X in the B space, and you can check in terms of these projectors and annihilation operators. These are then the correct expressions to write down. Okay? And then it's a very simple calculation to construct this combination C, which remember was A1 into B1 plus B2 plus A2 into B1 minus B2. And you construct this combination C and you compute its expectation value in the thermofield state, and you find this answer. Okay? And this answer is maximized at x equal to half, at which point C takes the value 27 square root 2 by 16, which is 2.4. And that's larger than 2. So this is already a violation of Bell inequalities. It's telling you that A and B are entangled. It's less than this value 2 root 2. Part of the reason is that we didn't take advantage of all the entanglement in the state. We just work for technical simplicity within this 0, 1 space of states. But in any case, this is going to be good enough for our purposes. Okay? So this is an example of how in simple harmonic degrees of freedom, you can easily construct operators that give you correlators that are beyond the classical limit. Okay, so now in quantum field theory, the idea is to extract simple harmonic degrees of freedom from the field and to extract them in such a way so that the vacuum looks, so we'll always now compute, all expectation values will now be taken in the vacuum. And the idea is to extract operators so that the vacuum looks like the thermofield double state for these degrees of freedom. Okay? And so how do we do that? So we do that first by just defining some simple harmonic degrees of freedom by taking the field and its conjugate momentum, and you smear that over a space-like separated region, and then you define these annihilation operators, alpha S. So one for you take the field, you smear it in two distinct regions, and one gives you alpha A, the other gives you alpha B, and you normalize these smearing functions so that these alphas have canonical commutators. Okay? And then you write down these operators A's and B's precisely as we did in the case of the simple harmonic oscillators, which remember was some combination of the projector onto states annihilated by alpha multiplied by alpha and alpha dagger. Okay? Okay. Now, in fact, for actual calculations, it's convenient to represent this projector as a linear exponential of x and pi, which are these smeared field operators. And you can check easily that the projector onto states annihilated by alpha s can be written in this form, where these t and theta are some dummy variables, and you're integrating over some linear exponential of x and pi. And kappa is this funny factor. It's twice the square root of tangent phi theta. This follows basically by carefully integrating out these dummy variables and taking care of the BCH lemma, which tells you that x and pi don't commute. So it's a simple formula to derive. And the advantage of this is that it allows this linear exponential term, which will be useful when we do actual calculations later. Okay. In fact, if you want to compute the two-point function, we have to compute these two-point functions of A's and B's, and the two-point function can be extracted from some generating function, which has two of these linear exponentials and then some other factors that let you pull down factors of alpha and beta. And so you can write down some generating function that will generate all two-point functions for you. And to actually calculate expectation values of these generating functions, it's useful to do a Bogoliubov transformation and write these alpha operators, which were our smeared field operators for our two systems, in terms of some global annihilation operators. And global annihilation operators, of course, are those that annihilate the vacuum. And remember, I said that we were working in the vacuum of the quantum field theory. So there are some functions, h and g, that tell you the transformation from global operators to these alpha operators. And then in terms of these functions, h and g, it's an easy exercise again to compute the quantum expectation value of this generating function. And the details are not important. In fact, I don't have all the details on the slide, but let me just point out some salient features. The expectation value of this generating function of 2-point functions only depends on the inner product, okay, where the inner product is basically taking these coefficients and summing them over all modes of these coefficients which relate these annihilation operators to the global creation annihilation operators. And then this quantum expectation value also depends on these dummy variables, but this dependence leaves you with an entirely Gaussian integral, which you can then do. In fact, you can do this for a completely general smearing function, but that gives you some complicated expression. And so I'm now going to describe how you can make some simple choices of smearing functions in global ADS to get simple values for these Bell correlation functions. Okay, so let me specialize now to global anti-de Sitter space. And so now everything I said so far would have been true in any quantum field theory. Now I'm going to specialize to global anti-de Sitter space. Just to set conventions, this is the setup in which this is my metric of global anti-de Sitter space. I'll be in d dimensions where d is arbitrary. Okay. And the way I'm going to construct these operators A and B is to start at some point in the middle of anti-de Sitter space, which is at t equal to 0 and some rho equal to rho naught, and then get these systems A by smearing the field inside this purple region, which is inside the light shell that emanates from that point, and get this system B by smearing outside the light shell that starts from that point. Okay? Okay, so more precisely, you can write down some precise smearing functions. And the idea behind these smearing functions is very simple. It's basically to try and extract Rindler modes on opposite sides of the light shell that starts at some point in rho space in global ADS. Okay? So if you look at what the smearing function does, this u is like a Rindler coordinate, and this factor basically pulls out a Rindler mode from the field. In fact, we'd like to be very precise, and we want everything to be finite, so you can actually evaluate this on a computer. And so to do that, we introduce some turning on and off function that starts this Rindler integral when you're a little bit away from the light cone, and then switches it off after a little while. In fact, you can switch it off pretty fast, and the reason for that is that this factor of u by u0 oscillates an infinite number of times near u equal to u0. So you don't actually need to do this integral for a very large region to extract the Rindler mode. You can do it for a small region around the light cone. Okay? That's in fact the reason why Hawking radiation doesn't care about the ambient curvature of the space. The entanglement of Rindler modes near the light cone is universal, and that's because of this factor that this factor u by u0 oscillates an infinite number of times near u equal to 0. Okay, so you can use this alpha s, which is the smearing function, which defines the systems A and B in terms of this field phi. Okay? And then you can write down this Bogoliubov transformation, which tells you how the global modes are related to these modes alpha, and that involves doing some integrals with these global modes. These global modes you can also work out for a minimally coupled scalar field in global ADS, and these modes are some hypergeometric functions. But you can do these integrals, and in the end you get some nice answer which says that these modes alpha and are written in terms of the global modes in terms of these kinds of Bogoliubov transformation functions. Okay? So there's some explicit. I'm just saying this not for all of you to get the details, but just to say that these are all steps you can carry through very explicitly. Okay. And then you can calculate this matrix of inner products, and you find that remember I said that when you wanted to compute these quantum expectation values, what was important were these inner products of these Bogoliubov coefficients. So you can calculate this matrix of inner products, and you get some nice matrix of inner products where x is related to this frequency that appeared in the definition of the modes, and then you get some nice matrix of inner products. And now at this point I want to emphasize that although this is a calculation that was done in free field theories, in fact, this calculation is robust against 1 over n. I mean, it's robust in that it's not corrected at leading order by 1 over n corrections. Okay? And that's because this is just a 2-point function. The thing I've computed is just a 2-point function. And so you could turn on finite n, and you would get 1 over n corrections, but you would not change this leading order term. Remember, at some point, I also said I introduced these cutoffs to make everything finite. So I started the smearing at some distance from the light cone and switched it off after some time. And so there's also dependence on those cutoffs, and I'll denote any dependence on those cutoffs by order epsilon. And the statement is that you get some leading order result for these 2-point functions, which is corrected by 1 over n and an order epsilon, but the leading order term is robust. Okay. Good. So now you insert this inner product matrix into this general formula I had for the 2-point function, and you find, and of course you have to find, because that's the reason I chose these smearing functions, that the entanglement between these modes outside and inside the horizon for this value of x being half is just exactly 27 square root 2 by 16. Okay? And as I just said a minute ago, this is a result that it's obtained by a free field calculation, but it's valid in any perturbative field theory, and the perturbations will just correct. If you turn on interactions, then that would correct this result by 1 over n and order epsilon. Okay? So this is the statement. So far I haven't done anything very complicated. All I've done is I've said in global ADS, you can extract pairs of simple harmonic degrees of freedom from a minimally coupled scalar field in a very explicit way. You can calculate, you can construct operators which have operator norms which are bounded by 1, and then you can calculate the 2-point functions, and you get the answer that you would get for 2 simple harmonic oscillators in a thermofield state. Okay? And this answer violates Bell correlations, violates Bell's inequalities, and gives you some answer between 2 and 2 root 2. Remember, this is about 2.4. Okay, good. So there are no questions at this point. So now I'm going to go on to gravity. Okay, so far what I said didn't require dynamical gravity. Now let me now consider the effect of dynamical gravity, which is the interesting physical effect that I want to describe. Okay? So the first thing I'll do is I'll allow the metric to fluctuate. So my metric, which is now an operator in my full theory, is the background metric, which I wrote down a few slides ago, plus some fluctuation, which I'll denote by h. Okay. And then I want to define this operator, which many of you will recognize as the canonical Hamiltonian, which is roughly the boundary value of h normalized by a factor of g Newton and some other factor that strips off the fact that this field dies off as you go close to the boundary. Okay? If you just use the standard extrapolate dictionary within ADS CFT, then you see that this factor, this operator, is really just the Hamiltonian of the theory. And in fact, in the canonical theory, this is the Hamiltonian of the theory if you just had canonical gravity. Okay? Now, maybe you might say that the extrapolate dictionary is corrected by 1 over n. In fact, we've only checked it at order 1 over n. But all I am going to need in the remainder of this talk is that this operator, this H canonical operator that I defined, that this is a positive operator, and it has a unique ground state. So it has a unique eigenstate with eigenvalue 0. And the other thing I'm going to need is that the overlap of this ground state of H canonical with the true ground state of the theory, or the ground state of the full Hamiltonian, is not even necessarily 1, but it's close to 1. Okay? It's 1 minus some order 1 over n terms. So in particular, I will not assume the statement that sometimes people make, that the canonical Hamiltonian coincides with the CFT Hamiltonian. I'm happy to let those things be different. Okay? The second part here is the fact that this canonical Hamiltonian has a unique ground state, and this is the reason I had to be in global anti-de Sitter space, which avoids any problems that one might have with infrared modes. Okay? So in global anti-de Sitter space, we really do believe that the vacuum is unique, and the vacuum is also the vacuum of the canonical Hamiltonian. Okay, let me make a few more comments on this projector. So once I take the canonical Hamiltonian, one second, I can now define the following operator, which is just take this canonical Hamiltonian and insert it into an exponential, and insert it into a very large exponential. And this gives you this operator p omega, and you might at first sight have thought that this operator p omega was a very complicated operator. It's an exponential of something. But in fact, if you just look at the assumption that I made previously and just think about that assumption, you will see that this is projecting onto the ground state of the canonical Hamiltonian, and the ground state of the canonical Hamiltonian is close to the ground state of the full theory. So in fact, we can treat this operator exactly, and this operator is just a projector onto the vacuum. Maybe it's a projector onto a state that's slightly different from the vacuum, but up to 1 over n corrections, this operator p omega is really just a projector onto the vacuum. Okay. Now, remember earlier in this talk, I defined what I meant by a localized operator. Okay? So by our definition of what we are calling a localized operator, this is just an exponential of the metric fluctuations near the boundary. So this p omega is a localized operator in the bulk theory near the boundary. And this is just our definition of what we meant by a localized operator. But in fact, there's a more physical reason to think of this operator as being localized near the boundary. And I know some people like this notion of having operational prescriptions to act with an operator. In fact, there's a very simple operational prescription to act with this operator p omega from near the boundary. And the way you do that is you think of an observer who has multiple identically prepared systems, and this observer also has some external measuring apparatus which is external to the ADS system. And then this operator just measures the energy of the system, which one can do sitting at infinity. That's how we measure the mass of the sun. So this operator in global ADS can measure the mass of whatever sits inside anti-de Sitter space, and just discards those experiments where this observer does not get the value 0. Okay? By doing so, given whatever state that you have, you can always act with p omega just from close to the boundary. So that's another reason to think of this operator as being localized near the boundary. Okay? Let me make some more comments on this projection operator. In fact, when I define this projection operator, I define it as a limit of this exponential. In fact, you do not need to take this exponential strictly to infinity. You can just take this exponential to be large. You can take it to be log n. And in fact, you can even expand this exponential out in a power series, and you can estimate how many terms you need to keep. And you need to keep n log n terms to get accurate correlators of p omega. And therefore, correlators of p omega, you can think of just as high point, multi-point correlators of metric fluctuations near the boundary. Okay? Always metric fluctuations near the boundary and not metric fluctuations anywhere in the bulk. Okay? So I've given you many different reasons to think of this projection operator as an operator that's localized in a naive sense near the boundary. Okay. Now, the fact that you can project onto the vacuum is what is special to gravity. This is not something that you could do in any other theory. In no other quantity. You have a question? Yes.
N log n, you think is small enough that you can still treat it near the boundary?
Well, n log n is, I mean, so remember when I talked about localized operations, I just meant taking a function of field operators from a given region. So these are just n log n operators. All the operators that appear inside that expansion have coordinates which are near the boundary. If you're referring to the fact that this operator is secretly non-local, that's certainly true, but it is localized in a naive sense of the word. It's localized in the sense in which I defined what I meant by localized, and I give you some other reasons why this is localized near the boundary. Okay, I didn't mean that n log n was small. N log n is large. Okay. So projecting onto the vacuum from near the boundary is of course only possible in gravity. In no other theory can you project onto the vacuum, because the fact that the Hamiltonian is a boundary term is something that's special to gravity. And so this is true, but the next step in this construction I'm going to present relies on the fact that in any quantum field theory, once you're given the vacuum, you can always lift it to any other state by acting with an appropriate operator from any region by acting with localized operators. And in this case, you can do it very explicitly. Okay? So how do you do this? So the idea is, in fact, there's a Rischlider theorem which tells you can do this, but I don't want to invoke any theorems, so we'll just do it explicitly. So the idea is that in global ADS, you think of a small causal wedge near the boundary of ADS, which is this green region here. And this causal wedge you can parameterize, was analyzed in detail by these people, and you can parameterize by some coordinates, rho and rho r and tr, and a hyperbolic d-1 dimensional space, which is dh-1 squared. And then you can extract, within this little green region, you can extract some wedge annihilation operators, which are these operators eta, basically by taking phi, this scalar field we've been talking about, and its conjugate momentum, and by integrating them with the appropriately normalized eigenfunctions. And so just by doing an integral in this green region, you can extract some wedge annihilation operators. Similarly, by doing an integral on the complement of the region, you can extract some other operators n tilde, which have the property that they commute with this, eta tilde, which have the property that they commute with this eta, and they're entangled in this particular way, in that the action of eta tilde on the vacuum is just e to the minus pi omega into the action of eta dagger on the vacuum, and vice versa for these creation operators. Now, this is something that follows from the Bisoniano-Wichmann theorem applied to anti-de Sitter space. But once again, I said I don't want to invoke any theorems. And in fact, these gentlemen in a paper earlier this year verified this result by explicitly working out all the Bogoliubov transformations and these correlation functions. So this is again something you can just verify in a very clean way, even if you don't believe that the Bisoniano-Wichmann theorem applies to anti-de Sitter space. Okay. Now, in particular, remember that I had these operators xb and pi b. So now I'm only talking about the system B, which was some smeared version of the field phi outside this light cone near the middle of ADS. Now, because these operators are just linear combinations of these 4 sets of operators, and that's because these 4 sets of operators give you a complete basis of modes for the whole space, therefore, you can write the action of this bi operator, which is made up of x, b, and pi b, on the vacuum in terms of some operator qi, which is made up only of eta and eta dagger on this wedge. Okay? So, of course, the operator bi is made up of eta, eta dagger, and eta tilde and eta tilde dagger. But the action of bi on the vacuum can be written as the action of some exponential of eta and eta dagger on the vacuum by using this set of relations. So this is again something you can check explicitly. Okay. Now, these operators qi again would exist in any quantum field theory, but you cannot directly use them in these CHSH inequalities because they are not bounded operators. But of course, in gravity, we have this projector onto the vacuum. And so you can combine these operators qi with this projector onto the vacuum, which I introduced previously, to construct these operators Ci. There are some coefficients here, but these are not operators. These are just some numbers which give you the expectation value of Bi in the vacuum. And you can construct some operators whose operator norm is less than 1. And this combination is in fact constructed to ensure that the operator norm is less than 1. Okay? And now these operators Ci are localized in this region, which is this brown disk plus this little wedge here. Your question, yes?
What distinguishes A and B that you use B in this formula?
Well, I chose to use B because I want to get entanglement with A. There's nothing, this is a choice. I'm defining my operator C this way. You could define a similar combination for B, okay? But I'm defining my operator with A instead of B, but I'm defining my operators this way. Okay. And so you get some operators whose operator norms are bounded by 1. Now, the interesting thing about these operators, if you look at this definition, it's easy to see that in fact the correlator of these operators with A is the same as the correlator of these of A with B. And the reason for that is the action of Ci in the vacuum is the same as the action of Bi on the vacuum. And therefore, its correlator with A is the same as its correlator with B. But we calculated the correlation functions of A with B, and we found that, if you looked at the expectation value of this CHSH operator of AB, you would have got 27 root 2 by 16. And therefore, if you take these operators Ci that I just constructed and you put them inside this CHSH combination, you find that CAC is also 27 root 2 by 16, just like CAB. Okay? In particular, that means that CAB squared plus CAC squared is twice of 27 square root 2 by 16 square, and this is 729 by 64, which is 11.4, which is manifestly larger than 8. Okay? So, by means of some operators which are localized in manifestly space-like separated regions, this region A, this region B, and this region C near the boundary, we violated this monogamy inequality that would hold for local quantum field theories. Okay? And this is just an explicit calculation in which every step along the way I try to emphasize that you could verify and check explicitly. Okay? Okay. So of course, there should be no paradox because we did all the calculations very explicitly, and so the resolution, which is probably obvious to many people in the audience, is just the fact that even though these operators A, B, and C are space-like separated, you can in fact check the commutators. Okay? And you can check that because of this factor of this projection operator P omega that lives inside Ci, the commutator of B with C is an order 1 operator. Okay? So even though you might have thought that commutators in gravity are small and they're suppressed by 1 over n, because P omega is such a complicated operator, it's the exponential of the Hamiltonian, of the canonical Hamiltonian, the commutator of B with C is some large operator, so some order 1 operator. And therefore, this paradox is of course not a paradox with the quantum information theorem, which is a theorem, but what it's telling us is that information that seems to be present in one region of space can sometimes be extracted from an entirely different region by a suitably complicated operation. And this is an explicit example of how that can be done in a completely controlled fashion. Okay, so my time is running out, but yes.
I mean, isn't it even simpler in the sense that before we look at this complicated operator, P omega inside of Ci, inside of P omega there's the Hamiltonian, which is a pretty simple operator.
Yes.
And it already doesn't commute with local operators in the bulk.
Yes.
And that's really what
that's correct.
From, right? So
That's correct, but the Hamiltonian by itself would not have given you, so somebody asked me this question. So of course you have to create a bounded operator. So if you just took the metric fluctuations and you computed like Giddings and Donnelly did, those commutators, you would get some commutators that are generally suppressed by the distance in units of L Planck, okay? Or actually L Planck divided by the distance between operators. So if you just took the metric operator, I mean these are these commutators that Giddings and Donnelly computed, and they're suppressed by E over M Planck, where E is the energy of the operators. So if you just took a simple function of the metric operators and you tried to violate this inequality, you might be able to do it, but you would get an order 1 over n violation. The thing about constructing a complicated operator is that you get an order 1 violation, even though the commutators of the metric with something inside are 1 over n. Okay? And so the interesting point here is not that you get some mild violation of the monogamy inequality, but that you get an order 1 violation, and which was the interesting point also in these paradoxes.
But I mean, the Hamiltonian has a 1 over G Newton in it, so it can pick up the tail, the gravitational tail that's proportional to G Newton of it.
That's right, but remember you have to make a bounded operator out of this.
Order 1. Yeah.
So, but you have to make a bounded operator. You're not just computing H with A. You remember the operators Ci have operator norms which are bounded by 1. So you see, there would have been no, if you were just trying to compute commutators, that wouldn't have been anything. You have to construct a bounded operator. So you can't just take a big operator and then say, oh, you can't multiply something by 1,000 and say, oh, the commutator is as large as you like. In the end, C is an operator which has operator norm which is bounded by 1. So it's not as trivial as just taking an operator and making it large.
Can I also think of this as due to gravitational resting?
Yes. It is actually happening because of gravitational resting in a secret way. And so the way I've combined these operators inside this projector onto the vacuum does in fact give you an order 1 commutator. And so you might have thought that this P omega is a localized operator near the boundary, because you can even act with it operationally from near the boundary. But in fact, because of this gravitational resting, it picks up what's happening inside. Yes, so you have a question? I just have a couple more slides. Can I, but go on please, yeah.
So what do you mean by although ABC, what do you mean although they're space-time separated? What do you mean that space, if I can violate this monogamy inequality, I can send signals supernumerally from my...
They're space-like separated in the sense I defined previously, in that I defined what I meant by a localized operator, which conforms to a naive notion of locality, which is that you can act with A, B, and C sitting in different regions. You can act with A in one region, act with B in a different region, and act with C by sitting somewhere else in a space-like separated region. So in that sense, they're space-like separated, this diagram. So C is defined by field operators from this region, but they don't commute.
And signals can be sent.
That is correct. So gravity does, so in a usual, that's a very unusual thing. In a quantum field theory, of course, that wouldn't happen. But in this case, it does happen. Can I just complete for 2 slides and then we can take this question? Okay, let me just finish. Okay. So one of the points I wanted to make is that both these strong, if you think carefully about the strong subadditivity and the cloning paradoxes, both of these paradoxes in fact make reference precisely to complicated operators of this kind. You can estimate how complicated the operators have to be to get these paradoxes, and it's easy to estimate. You need to extract an S-point correlator from Hawking radiation to come up to these paradoxes. And in fact, if you make some simple estimates, this is also precisely the threshold if you try to measure an S-point correlator of Hawking radiation at which you might expect these non-local effects to be important. So measuring the operators that lead to the strong subadditivity or the cloning paradoxes is precisely like measuring this complicated operator Ci. Okay? And this suggests and I think the Stoy model suggests that therefore, you can resolve a lot of these, you can resolve both the strong subadditivity and the cloning paradox just by recognizing that what you would think of as a localized operation, in that you might think that you're collecting the Hawking radiation far away and you're doing some operation far away, but really that naive notion of a localized operation just doesn't work in gravity, as you see in this simple example, and might actually correspond to something that's secretly very non-local. Okay? And the other point I want to emphasize is that this is not something that's mysterious or special to black holes. It's an effect that appears already in a control setting in empty space, as we see here. Okay. Now I think there are many interesting open questions. First of all, it's not true that if you do complicated operations, all bets are off and everything just becomes arbitrarily non-local. In fact, if you look at the literature on subregion duality, that tells you that if you're sitting inside one entanglement wedge and you do arbitrarily complicated operations inside that entanglement wedge, they don't leak outside the entanglement wedge. They remain confined to that entanglement wedge. Of course, in this case, and in the strong subadditivity and the cloning paradox case, you have to surround the black hole with a sphere and make measurements all throughout the sphere, and that's not the entanglement wedge of anything. Okay, so I think there's interesting open questions about when these non-local effects are important, but I think it's clear that in some cases they are important, as in this toy model, and I think this strongly suggests they're also relevant for black hole evaporation. Okay, so this is all I have to say. I'll stop here and take more questions. Thank you.